Alright, so what we're going to do in this tutorial is we're just going to basically produce the analysis that we saw in the previous tutorial. So that was obviously this part here, where we had it loaded at one end and we had a downwards pressure acting on it in the sort of lug on this circular section here on the bearing surface. So we're going to start from scratch. We're going to produce the geometry, apply the material and section properties, create the loading step and actually applying the loads and boundary conditions, as well as doing the meshing and then reviewing the results. So that's what we're going to look at today. So you can see here we have our part. It has a height of 50 millimeters. It has a width from the edge to the center of the bearing surface of 100 millimeters. The bearing surface itself has a diameter of 30 mil and the part is 20 millimeters thick. So that's what we have to produce. So I'm just going to jump over to Abacus. So just make sure you're at this screen of Abacus and we can get started. So when we are developing our analysis, the easiest way for us to make sure we're doing all the correct steps is to basically just follow from the top of your model tree down to the bottom, and everything that you need to do will be inside of that process. So the first thing I'm going to do is right click on part, and I'm just going to hit create because we're going to create our part. So it's going to be a three-dimensional part because we had the 3 dimensions of our drawing. It'll obviously be deformable. We'll just make it using solid elements because that's what we saw in the previous analysis, and how we're going to make it. So we have different options you can make it. So what we're doing here is we're going to create a sketch. So we're going to create sort of this profile of a sketch, and then we're going to extrude it through that 20 millimeters. If you had other geometries, you could do a revolution or do a sweep, depending on what shape you were trying to generate. Again, Abacus isn't the best interface for actually developing your CAD. If you're going to use complex CAD, complex geometry, it's better to bring it in from your CAD package of choice. So we'll just hit, actually before we do that, we're going to be using SI units. So SI units are obviously meters, seconds and kilograms. And we can see that these dimensions here are in millimeters. So our dimensions aren't going to be, for example, 20 millimeters, it'll be 0.02 meters. Now the approximate size of our part isn't going to be 200 meters in size. The approximate size may be something like 200 millimeters, which is 0.2 meters. So I'm just going to change that to 0.2 and we can get started. Now you can see the reason we've done that. If I just click on this button here, right, and as I hover over my viewport, you can see up the top right here we have the X and Y coordinates, and you can see the far left hand bound is 0.065 and the far right hand bound is 0.65. So what setting that initial approximate size to is it just puts in the appropriate bounds into your viewport. So the first thing we're going to do is we're going to create the outside shape of our geometry. Now, just like with CATIA or SolidWorks or Creo, this is a parametric modeler. Obviously it's not quite as powerful as other parametric modelers, but the idea is you put in your geometry and then you can define your dimensions later on as parameters. So what I'm going to do, I'm going to create an outside rectangle. So I'm just going to click on this rectangle button here. I'm going to click to approximately that size. Now I could sort of drag it wherever I want, or I could go down the bottom here and enter in a specific X and Y coordinate and hit enter, but I'm just going to drag and click again to get my size. Now I want to change the dimensions on this, so I'm going to go to this dimension button over here and click on that line, and I know from my drawing I want that to be 50 millimeters, which is obviously going to be 0.05 meters, and I can just zoom out, and I want this length here to be 100 millimeters, so I can make that 0.1. Again, just changing your dimensions down the bottom left hand corner here, and then I can just hit enter to apply that. Now I know in my drawing I don't have this line here, so what I'm going to do is I'm just going to use the erase tool, and I can just erase that line and then hit done down the bottom, and that gets rid of that line. On the end there, I do know that I have a arc that goes from tangent from this line around to tangent with this line, so I can just click this create arcs. So we have a number of different ways we can create arcs, but I'm just going to use this this one here, which creates an arc which is tangent. So if I click on this one, you can see I now have a tangent curve, and when I bring it around there, then it also forms tangent, so that's right size. Looking at my drawing again, I can see the last thing I need to put in is this 30 millimeter diameter hole. So I can just go in here, and you can see here that because I've put in that arc, I now have a center point of that arc, so that already gives me the central location of that hole. I can do that, and the last thing is obviously for me to dimension up that hole, so I can just go to my dimensioning tool again, click on it, and it's wanting me to add in a radius. I know that because it's saying R for radius. So it's a 30 millimeter diameter hole, so that's a 15 millimeter diameter, radius, 15 millimeter radius hole. Right now, and that looks all good. It has moved a little bit in space, but it's all good. Everything, all the other dimensions, all the other constraints have kept it in place. If you have any problems, just stick your hand up and we can then get the tutor to help you out. So we've added all our dimensions in. Simple, normal CAD stuff. If you've done any CAD work before, this shouldn't be too difficult. And the last thing we need to do is just put in our extrusion depth. Remember, we've already said that this is an extrusion. So the last thing we need to do is go down the bottom left-hand corner here and just hit this X. And then say done, and then it'll ask us what extrusion depth do we want to go to. And as we said, we want to do it 20 millimeters, which is going to be 0.02 meters. And I can just hit OK, and then that gives me my geometry. So that's just the simplicity of creating geometry in Abaqus. Again, Abaqus isn't the greatest method for developing geometry, particularly if you've got complicated geometry. It's good to be able to figure out how to get it from CATIA or SolidWorks, whatever you're modeling in, through to Abaqus. And Abaqus can import in a number of different file formats, and later on in the semester we'll actually go through that and show you how to do that as well. Alright, so I can just continue going down my list. The next thing I'm going to do is, as I said, we're just going to keep going down this model tree. I'm going to right click on materials and hit create. This thing's going to be made out of steel, so I'm just going to change the title, the name to steel. Now to add properties, we're just doing a simple basic structural analysis. So for that, there's only two properties you need. You need the elastic or Young's modulus, whatever you want to call it, and we also need the Poisson's ratio. So these are the two basic parameters you need for a linear elastic analysis. So you can find those under mechanical, and under elasticity we get elastic properties. And you can see here down the bottom now we only have to define the Young's modulus and the Poisson's ratio. So remember we said last time that there aren't any particular units associated with Abaqus, unlike some other FEA packages. So it's only the units that the user is using. So that means the Poisson's ratio, the Young's modulus for steel is about 200 gigapascals, and remembering that we're using SI units, so I can just put in here 200 gigapascals in SI units is just 200 by 10 to the power 9, so I can just put in E9 for exponent 9. I can move across the Poisson's ratio, and Poisson's ratio obviously doesn't have any units, so I can just put that in as 0.3 for steel and then hit OK. So what we've done there is we've defined a material, but that material really isn't associated yet with anything else. We haven't said that this block is made out of steel. We haven't even said anything about that particular block itself. So what we're going to do is go into sections. And we're going to create a section. So what a section is essentially, it tells Abaqus, it tells it a few different things. It tells it what type of material we're looking at, as well as the actual material properties of that section. So we're going to call this one lug, because this is our lug section. The material is going to be, it's obviously a solid material, and it's going to be homogeneous. It's going to have all the same material properties throughout itself. We can hit continue, and we're just going to say it's obviously being made out of steel. Now we only have one option For us, if we made other materials, we can choose them from here. Additionally, to the right, you can see there's this create material button. So if you already hadn't previously created a material, you can just use this as a shortcut again to access that material creation functionality. And we'll just hit OK. Alright, now again, we've created a section which is a homogeneous material, and we have the steel material properties added to it. But still, we don't know, we haven't told Abacus that this object that I'm seeing in front of me, this lug, is associated with that section. So it doesn't yet know that it's homogeneous, and it doesn't yet know that it's made out of steel. So what we need to do is, if we go down again and go to the tree, if we go to the part, and if we just open that up, so we only have one part in there at the moment, which is our lug. So we just want to open that up, and you can see down here we have section assignments. So this is where we can tell Abacus that the section that we just created should be used to define the behavior of that particular part. So I'm just going to, again, I could right click on it and go create to create a section assignment, or I could use these commonly used features over to the right hand side here. You can see here we have create section as well as section manager, and then we have assign section as well as the section assignment manager. So I'm just going to click on this one. You could click here, or I'm just going to escape, or you click on the section assignment manager, which will bring up this tab here, sorry, this window here, and I'm going to hit create. Now you may be wondering, okay, what has happened? But now you can see when we hit that create button down the bottom there, we have a prompt telling us select the regions to be assigned to a section. The region is simply just going to be this part, and when it highlights in orange, and then we can say done, and we are going to apply that lug section that we just created. And we can see here, just for our confirmation, that it's a solid homogeneous object which is made out of steel. Excellent, so that's all we need to do for that now, and I can just get rid of this window by hitting dismiss. Alright, awesome. So now we have made a part which has the right geometry, and we've said that's a solid homogeneous material that's made out of steel. Now the next thing we need to do actually is that we need to put that particular part that we've just created into our analysis. So we need to do that via this assembly tab here. So if I just open that up, we can see here we have another different options, and we'll go through this as we go through semester. But I'm just going to right click on instances and hit create. So what this is doing now is basically you can have multiple different parts underneath your part list over here to the left, but it doesn't necessarily mean that all those parts that you have in there need to be active in a particular analysis. The way that we tell Abacus whether a part is active in an analysis or not is via creating assemblies and instance assemblies. So we're going to create this instance when we're going to create it from a list of parts, and the only part we have available obviously is the part that we have generated thus far. And then we have two options here down the bottom. Now we'll get onto meshing, as I said, further on in the semester, but we just know that we have two options here. We can either have a mesh which is defined from our part, so up above here, or we can define our mesh for each particular assembly instance. Now we've only got one assembly here, and we've only got one part, so I'm just going to choose dependent for the moment, but we'll show you later on in the semester what we can do with independent meshes. And we'll just hit OK. So you can see here now that that has created an instance here where it now has a number 1 next to it, where that is essentially where we're going to be putting our loads into. Now before we go and create our loads, we're going to keep working our way down this model tree, and the next thing we have here is steps. So you can see here when we open that, we haven't added anything in yet, but we can see already there is one step applied in there, and that is the initial step. So this is a default setting for Abacus, and the initial step essentially is a zero action step. In that initial step, nothing happens. There are no loads applied, there are no boundary conditions. It's essentially just having the assembly in space. It's good practice not to add any loads or boundary conditions into that initial step. What you want to do is create a secondary step where we go and apply loads and apply boundary conditions. So what we're going to do is we're going to right click, or you could, we're going to right click on the steps and hit create. And we're going to call this one I'm going to call it load application. So I know what it is. Now again, we have a number of different options to us. We're not going to address most of these. We're not going to address hardly any of these considerations. Most of the analyses we're going to do in this subject will be static analysis. That means there is no inertia to consider, and it's a general analysis, which just means it's a general structural analysis. And we can hit continue. The description of this is going to just be load application again. That's what's going to happen in this step. Now it asks us for a time period. The time period here doesn't particularly matter because, as we said, it's a static analysis. There is no inertia being taken into consideration. All that happens, well, all that means is that at time 0, which will be the end of the initial step and the start of the load application step, we will have 0% of the load applied. At time 1, we will have 100% of the load applied. Now again, when you think about time, don't think about it as actual physical time. Think about it as sort of a percentage of how much load is being applied. Remembering obviously that inertia isn't taken into as a consideration here. And I'm just going to, so we'll just leave that as 1, and we can leave everything else as default and just hit OK. Okay, so now you can see here that we've added in the load application step, and it's actually been underlined. When you see the thing being underlined, it just means that that's the particular active element at the moment. So at the moment, the element which we are going to be adding in loads into is the load application step. So we can just go down to further down. Oh, actually, while we're heading down that way, we're just going to, we'll come back around that later when it makes more sense. So what we're going to do now is, while we've got that load application step active, we're going to jump down into the loads and the boundary conditions down the bottom here. So if you remember from our previous analysis, we had this backhand surface here fully fixed. So out of the 6 degrees of freedom, all 6 degrees of freedom were constrained so that there was no motion of this surface at any time. And then on the inside surface here, we had a downwards pressure on the bottom surface. So what we can do is we're going to add in our fully fixed Castro boundary condition. So I'm just going to go right click on the BCs and hit create. And this is going to be the fully fixed end. It's going to happen in the load application step, and it's a mechanical boundary condition. Now we have a number of different types of boundary conditions, which are essentially just quick steps to reducing or changing, in effect, the numbers of degrees of freedom, or controlling the degrees of freedom. But I'm just going to select, because it's fully fixed, that's the Incastra boundary condition. So I can see continue. And then I'm going to select which boundary I want to apply this boundary condition to, which is just going to be this surface, and I can hit done, and then you'll pop up with this window here. So here you can see a number of different options available to us. So the first one there is X symmetry, which says that U1, UR2, and UR3 are equal to 0. So what does that mean? So remember we said in the last tutorial that the one direction is the direction here shown by X in this yellow coordinate system. The 2 direction is Y, and the 3 direction is Z. U just means linear displacement, so translational displacement. So that means this if we selected this one, for example, we would have 0 translation of that surface in the X direction. and we would also have 0 rotation in the 2 and 3 directions. So UR2 is the rotation of this surface about the y-axis, and UR3 is the rotation of the surface around the z-axis. So that's what UR means, is the rotation around a particular axis rather. Now we said for that surface we want it to be fully fixed, which is obviously this one down the bottom here, which has all displacements, so U1, U2, U3, as well as UR1, UR2 and UR3 all set to equal 0. So that means it's fully fixed and no nodes on that surface will be allowed to move. So I'm just going to hit OK. Excellent. So that's our fully fixed boundary condition. Now the next thing we have to set up is that we want a load being applied on this surface here, but we don't of a pressure pulling it down of 50 megapascals is what we're going to apply. Now we don't actually want it to be the pressure to be applied on the full surface all the way around, because if we did that, then that would mean that essentially it'd be a hydrostatic pressure and would have equal amounts of pressure poking in every direction, and it wouldn't be pulling us down, pulling the lug down. So what we need to do is we need to do a bit of geometry manipulation so that we can select not that entire surface, but just the bottom half of that surface, which is what we're going to do now. So if we just go, the way we can do that quite easily, remember we defined our geometry right back up in the part. So we just want to basically go back into that context and edit the geometry a little bit. So if you just right click on part 1 there and you say make current, which allows us to go into the editing tools for that particular part. Now down the commonly used tools over here, what we're going to use is this define cutting plane here. So what this is we're going to define a particular plane in space, which is going to be used to cut this lug in half so that we can select that bottom surface. So we'll see what I mean in a sec. So we're just going to click on that one, and it gives us a bunch of options. We can do it via a particular point and a normal. We can do it via 3 points or a normal to an edge. Now the easiest way for us to do this here is via this 3 points technique. So remembering that a plane, if you have 3 points in space, you can always fit a plane between them. So we're just going to choose that particular option. Now you can see here we're given a number of different options. It may depend on how you did your geometry as to which dots you see. But for myself, what I'm going to do is I'm going to choose this point, and this point. So you can see when I do that, each point goes selected from yellow to red. And when I've clicked on 3 different points, and you can imagine if I put in a plane between those 3 points, it would be essentially acting midway through my object in the XZ plane. And when I select the 3 of those, I can just go and hit create partition, and we're done. And now we can get out of that and just hit done. So you can see there that now I can select that bottom half of my surface, which was relatively easy to do. So now we can go back down to loads, and we can actually go right click on that and say create a load. So this is going to be, I'm just going to call it the pressure load. And obviously we want to apply a pressure, and we're going to hit continue, and I'm just going to rotate this so I can see this particular surface here, which is the surface I want to apply it to, and I'm just going to hit done, and it's going to ask me how I want to apply this. I want a uniform pressure, so I want a pressure which is uniform all the way across that surface, and I want it to be 50 megapascals, as I said earlier. Now 50 megapascals in SI units is obviously just 50 E6, and everything else will be fine. So when it says ramp there, what that means is, as we're talking about the load step before, So at time 0, it's going to be 0% of this 50 megapascals, and at time 1, it's going to be 100% of that 50 megapascals. So I can just hit OK, and you can see here now we have those purple arrows just indicating to us that we are applying that pressure. Alright, now we only have a few more steps to do, and then we can go solve the job. The next thing we need to do is we actually need to go and develop our mesh. So the way we develop a mesh, so remember we said earlier that when we created our assembly instance, that we said the mesh is going to be dependent on the part. So that means we actually need to develop the mesh inside of the part itself. So we're going to go up to the part, and if we open that up, you can see here we have the tab there for the mesh, for generating the mesh. So I'm just going to right click on it and go switch context. Okay, now we have a bunch of different options available to us here in the commonly used features toolbar. Now, I'm just going to show you a couple of things. So we're going to get more into the mesh as we go through semester, so I'm not going to go into too much detail about this, particularly as we're dealing with a solid mesh here and not a truss or a shell mesh. But I'm just going to click on mesh part, which is just going to apply the default mesh. So we just say, is it okay to mesh this part? And we can say yes. So you can see here that that's developed a mesh which is relatively coarse. Now, the way we can know that is that if we look at, for example, this is, if I switch context back to the part, you can see that the circle here, that's supposed to be perfectly circular. But if I go back to my mesh, if I right click on mesh and go switch context, you can see now that the mesh is relatively coarse and doesn't actually represent the curvature of that circle. So how do we decide how many elements is appropriate? Well, that's what we're going to be spending a lot of the semester on determining. As I mentioned in the lecture, part of this comes down to calculation verification. So we need to make sure that the outcomes of our simulation is not necessarily dependent on how many elements we have used in our simulation. That we have enough elements in there that it's accurate, but not too many that it takes forever to solve. One thing we can note down the bottom is we have generated 142 elements on our part, which is not particularly many at all. Yeah, so what we're going to do to change that up is we're going to go here up to seed part. So what seed part does is allows us to sort of specify to Abacus how many nodes approximately, or what's the average size of the element in our model. Now, at the moment, we currently have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements around the diameter of our part, around the diameter, or circumference of our circle feature there, and I probably want about twice as many. So what I'm going to do, you can see at the moment the global approximate size is set to 0.01. I'm just going to change that to 0.005, which is 5 millimeters, and hit apply. You'll get this little prompt here saying that, oh, you've already generated a mesh and you're trying to put in a seed, you might need to delete the mesh, and we're fine with that. We're getting rid of the mesh anyway, so we just hit delete, and I'll just hit OK there, and then we can go and mesh the part again. It says, do we want to mesh the part? We say yes, and then we generate this mesh here. Now you can see that this has 1,000 exactly one, or mine has exactly 1,000 elements in it now, which is obviously around sort of 7-ish times what we previously had with 142, even though we only had half the element size. This is obviously due to the fact that we have a 3-dimensional feature, so we double the amount of elements, so it's roughly going to be 2 cubed because working in 3 dimensions, 2 because it's double, well, it's half the element size, and cubed because working 3 dimensions. 2 cubed is 8, so this is roughly 8 times the number of elements, roughly speaking, so that's sort of how that works. Additionally, because we have now 1,000 elements, it's obviously going to take a lot longer to solve than it would do if it was just 142 elements. Now, still, this simulation won't take long to solve particularly, But just note that as you add more elements into your system, the longer it will take to solve. The rough rule of thumb that you can use is that if you double the degrees of freedom, then you will multiply the solve time by 4. Very rough, it's more so down to about sort of 2.8-ish, but we'll get into that when we go throughout semester. When we go through the lectures, we'll show you why that is the case. Now, we're not done yet here because we haven't really told Abacus. We've said that to Abacus, okay, these are the elements this is the mesh that we want, so this is the mesh that we want, but we haven't told Abacus what type of elements these are. Now, again, this is something we'll get into more detail as we go through a semester, but just note that in addition to specifying what the mesh is, we also need to specify what type of elements we want to use. So the way we do that is we go over here to assign element type. Now we just click on, we could highlight both parts of our body, of our log, so just make sure that you have not just bottom or not just top, but you have both parts, and we can hit done, and then we can tell what type of element we're going to use. So we're going to use, we want a 3-dimensional stress element, and it can be standard and linear, and we're just going to use the defaults here for the moment. And again, later on in the semester we'll talk about why we choose different sorts of elements. And we are done. So that's it. So we have gone through and we have created our geometry. We have created a material model and we've assigned that to a section, and then we've said that this lug part has that section assigned to it. We have created an assembly using the part. We have created a new load application step, and then we applied our boundary conditions to it, and finally we have just gone and made our mesh. The last thing we need to do is to tell Abacus what sort of outputs we want. If you didn't, well, Abacus puts in some default outputs, but by and large, if you don't tell Abacus what sort of outputs it wants, what sort of outputs you want, it's not going to provide them for you. So the way we do that is we go down to field output requests, and we're just going to right click on that and hit manage. So you can see here that it's saying, okay, we already have one output request attached to your simulation, so it's going to hit edit and see what's inside of that. So you can see here we have a number of options already picked for us. So for example, it's already giving us some stresses, some strains, some displacements, as well as velocity and accelerations, some forces and reactions. So we'll be able to figure out what force reactions we're having on the boundary condition, and we're also giving contact information. Now obviously we don't have contacts. There is only one body here, so it's not going to be in contact with anything else, so we're actually going to get rid of that. And we're not going to be interested in strains today either, so we just want to have a look at the stresses, the displacements, and the reaction forces. And we can just hit OK, and then hit dismiss. Alright, now if all that is done, what we need to do now is just go ahead and set this thing up to solve. So we did that, we go further down our tree, and then we get to the analysis section, and we have jobs. You just right click on that and go to the manager, and we're going to go create a job. So this is going to be the log solve. I can just call it log actually, and again you can just add in a description. I'm going to call it log solve. Don't worry about setting anything else up, and then we can just, that job is sitting there. Now if we don't click anything else, the job actually won't solve, so we just need to hit submit to submit that particular job. Now down the bottom here, we can see what's happening with it, or you can go onto your manager and hit monitor, and that'll bring up this screen here, which basically is just a readout of what's happening. And you can see here that it's saying it has completed this job, it completed the first increment, blah 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 blah, so everything looks good. So I can just dismiss that, and it also prints out some of that information down the bottom here in the prompt section. Alright, so now we're just going to review our results. So you can just see down here in the job section, we created that log job and it's saying that it's completed. So we can just right click on that and go to the results. And that brings us over to this other screen here. Now you can see the model tree has changed, but we can simply get back to that between these two tabs at the top here. Alright, so what we're going to do is we are just going to look at some of the results, as you said. As you showed in the last tutorial, we can click on this button here to bring up the contoured results. So this is obviously the von Mises stress, because we have S selected. So S is for stress, U is for deformation, RF is for reaction forces, and we're looking at the von Mises stress, for example. Now, again, these two fonts are illegible, so I'm just going to quickly change those so I can actually see them properly. That is in... Oh, it's in, sorry. That is in viewport annotation options, and so you can just go to that. I want my legend just to have a bit bigger of a font, as well as my title block and my state block, just so I can read everything. Okay, so you can see here again we have a stress of about 322 megapascals up in this zone here, and the same thing down the bottom here. Now it doesn't obviously say whether this is a compressive stress or not, because von Mises doesn't contain that information. Von Mises is an equivalent stress factor. Now we can look at other results if we wanted to. For example, we could go and look at the maximum principal stress. Now the maximum principal stress obviously will show you whether it's compressive or tensile. So if we look at this one, for example, we can see that in the red section we have a tensile stress because it's positive, and down here in the dark blue we have a compressive stress, which is blue down here because it's negatives, therefore it's compressive. Now we can look at it with this. Now obviously, the von Mises stress is a scalar stress. The maximum principal stress is a vectorial stress. So not only does the maximum principal stress have a value, but it also has a direction. And the way we can look at the direction of the maximum principal stress, which is obviously the most tensile stress in a particular area, is we can go down here to plot symbols. All right, so we can see here that we're seeing some arrows, but we can see that the green section of our shape is actually hiding these other arrows. So what we want to do is we want to make this solid section essentially see-through. So we can do that by going up to Common Options and changing our render style to wireframe. And if you just hit apply, then that shows you what we've got. So we can still see our elements, but it's now see-through. So what we can see is that up the top left-hand side here, that as we expect, as this circle is being pulled down, that a tensile stress is being imparted onto these elements up here. They're very largely tensile. And then we can see sort of the direction of that stress as it goes through the body, sort of comes down here and is going this way, whereas these stresses here, so the tensile stresses are obviously pulling outwards, whereas the compressive stresses, I don't know if we can see them properly, but you can see that the compressive stresses are pointing in towards one another. So they're the compressive stresses down the bottom there. Now, if instead of looking at the maximum principal, if instead we looked at the minimum principal, obviously the boundary condition down the bottom left here is going to be very compressive. So we can see here that the compressive stresses are much larger in the minimum principal down the bottom, whereas the max principal ones were obviously larger in magnitude up the top. which is obviously because this side's going to be in compression, this side's in tension as we pull this section down. We can look at other stresses, so stress 1-1. Now stress 1-1 is obviously the stress in the 1-1 direction, which is the stress acting on the face normal to the 1 direction, which is obviously the x direction. So the stress acting on the face normal to the 1 direction, acting in the 1 direction, if that makes sense. So S11 is a normal normal stress acting in the 1 direction, which is obviously x direction, which is why we see all these vectors acting in the x direction. If we wanted to look at the vertical stress acting on our system, that's obviously the stress acting in the y direction, which will be the 2 direction. So we want to look at the S22. So here you can see that we have some tensile vertical stresses, and down here we have compressive vertical stresses. On the top and bottom of around the circle we have compressive stresses, and on the left and right we have tensile stresses. We can also look at the reaction forces. So you can see here we're looking at the resultant reaction force, which is the overall reaction forces, which gives you both the magnitude and the direction of our results. Or we could just look at the reaction force in the x direction, that is the 1 direction, the 2 and the 3 directions. Obviously you can't see 3 from this view because 3 is in the z axis. So this stress acting here, this reaction force is only reacting because it's trying to resist the expansion due to Poisson's ratio. So we can have a look at all those results there. Now you can keep playing around. There's a bunch of other tools. I might just quickly go back to a shaded view. And I might, for example, bring up the stress. We might look at, I'll actually go back to contours. So in addition to normal stresses, we also have shear stresses. So we can look at the values of, for example, S12, which is the shear force in the 1-2 direction. So that's either acting on the face normal to the 1 direction in the 2, but acting in the 2 direction, or the face normal to the 2 direction acting in the 1 direction, because S12 is equal to S21. So we could have a look at those shear forces. And now obviously you can't look at those shear forces vectorially because it doesn't really make sense in that instance. But yeah, you can look at all those stresses, and you can also look at things like displacement. So if you look at the magnitude displacement, we can see that obviously this end here has displaced the most by 400 micron. You can look at that result, and the last thing we'll quickly look at is you can do animations as well. So I can do that. That's actually moving way too quick, so let's have a left hand side here. So you can just go to the animation options, and if I just slow that down and hit play, you can see how we can look at the animation of that. Now obviously this is scaled, so down the bottom here you can see the scaling factor of 29, and I can go you can change that by simply going up here and going to deformation scale factor, and just make it uniform and change it to a value of 1, and this would represent what deformation we actually would see. So that you can see that why it comes up with an automatic scaling factor of 29 is because when we set the scale factor to 1, you basically can't see what deformation is going on. Okay, now that brings us to the end of this particular tutorial. In the next tutorial, what we'll be looking at is just we'll be doing a basic truss analysis, and we'll be talking a little bit more about technical stuff through that process. Thank you very much, and we'll see